In this lecture, we're going to introduce the concepts of enthalpy and continue working on how to retrieve these values from the tables. So enthalpy is the sum of internal energy and the product PV. So our enthalpy is our internal energy plus PV, which is flow work. So you can have enthalpy on a mass basis, so your specific enthalpy would be your specific internal energy plus your pressure times your specific volume. You can also have it on a mole basis, where your molar specific enthalpy is your molar specific internal energy plus pressure times your molar specific volume. And the units are the same as internal energy. So the tables in the back of the book provide information on your internal energy, your enthalpy, and entropy, which we'll introduce in chapter 6, in addition to your specific volume. Data for internal energy and enthalpy is found the same way as specific volume. So for example, if you were in a two-phase liquid vapor dome, your specific internal enthalpy is going to be your specific internal enthalpy of your saturated liquid plus your quality times the difference in your specific internal energy of your saturated vapor minus your saturated liquid. The same goes for enthalpy. And actually, this quantity for enthalpy is called HFG, and it's tabulated. It winds up being a unit that it winds up being a quantity that we use quite often. So we decided, I don't feel like doing math, I'm going to put it in a table. So we're going to look at an example. This is example 3.3. We have a 10 cubic foot rigid, well-insulated tank that contains saturated water vapor at 212 degrees Fahrenheit. The water is rapidly stirred until the pressure is 20 psi. We want to determine the temperature at the final state and the work for the process. So the first thing that we need to do in order to find our temperatures and everything are to we're going to fix our state. So we're going to write down all the information about our state. So what do we have for state 1? Well, for state 1, we know that we have saturated vapor at 212 degrees Fahrenheit. Saturated vapor means that our specific volume is equal to our saturated vapor specific volume, which means we would go to table A2E and look up our temperature, and at 212 degrees Fahrenheit, our saturated vapor specific volume is 26.8 feet cubed per pound, and our internal energy, which is equal to our saturated vapor internal energy, is equal to 1,777.6 BTUs per pound. So for state 2, we know that P2 is equal to 20 psi. I'm going to start by going to table A4 and looking up P is equal to 20 psi. And what we also know is that this is it's a rigid tank, which means my specific volume at state 2 is equal to my specific volume at state 1, which is 26.8 feet cubed per pound. So I'm going to go to table A4. I'm going to look up a pressure of 20 psi. I'm going to look for a specific volume of 26.8. And if I interpolate, I'm going to get T2 is equal to 445 degrees Fahrenheit. And my specific internal energy at state 2 is 1,161.6 BTUs per pound. So we've achieved our first goal. We've determined what our temperature is by reading it from our tables based on our specific volume. Now I'm going to do an energy balance. We know that our change in internal energy plus our change in kinetic energy plus our change in potential energy is equal to our heat minus our work. There's no changes in kinetic or potential energy since we have no moving parts, nor is the system itself moving. It's also a well-insulated tank, so there's no heat transfer. So our work is equal to the opposite of our change in internal energy, which is equal to our mass times our change in specific internal energy, which is U2 minus U1, which is equal to, well, we don't know our mass. How can we find our mass? Well, we know the total volume is equal to 10 feet cubed, and our mass, our specific volume is our volume divided by our mass, so our mass is our volume divided by our specific volume. So if I take my 10 cubic feet and I divide it by my specific volume, I'm going to get that my mass is 0.373 pounds. So if I go back to my work is equal to minus 0.373 pounds times 161.6 minus 1077.6 BTUs per pound. So my work is equal to minus 31.3 BTUs. Again, the main difference between chapter 3 and chapter 2 was that in chapter 2 we had to be given some other piece of information to be able to figure out our internal energy change. Do another quick example. We have R22 undergoing a constant pressure process from saturated vapor at 4 bar to a final temperature of 30 degrees Celsius. We can neglect kinetic and potential energies. We want to find the work and the heat transfer. So the first thing I want to try and do is fix my states. So for state 1, I have saturated vapor. I have my pressure is equal to 4 bar. My temperature is equal to my saturation temperature, which is equal to minus 6.56 degrees Celsius. My specific volume is equal to 0.0581 meters cubed per kilogram. And my internal energy is equal to 224.24 kilojoules per kilogram. What do we know about state 2? Well, it's constant pressure, so P is equal to 4 bar. T2 is equal to 30 degrees Celsius. T2 is greater than Tsat, which means we are superheated, which I'm going to go to the superheated table for R22. I want to look up my pressure and my temperature. I want to find V2 is equal to 0.06872 meters cubed per kilogram, and U2 is equal to 245.73 kilojoules per kilogram. So my work per unit mass is equal to my pressure times my change in specific volume, since it's a constant pressure process, which is 4 bar times 0.06872 minus 0.0581, which is, let me correct my units. I'm going to wind up with my work being equal to 4.248 kilojoules per kilogram. To find my heat transfer, I'm going to do an energy balance. Since there's no changes in kinetic or potential energy, I wind up with my change in internal energy is my heat minus my work. So my heat per unit mass is my change in specific volume plus my work per unit mass, which is equal to, I'm plugging in my numbers, I get my heat transfer per unit mass is equal to 25.738 kilojoules per kilogram. In our next lecture, we are going to introduce the concepts of specific heat, specific heats, and also how to evaluate properties for incompressible substances and solids and liquids, leading up to introducing the ideal gas model.